thank you so much. And I wanted to thank the organizer for inviting me to this stimulating workshop. Today I will talk about our efforts to push calculations of electron-phonon interactions to the strong coupling limit, which is a major theme for this workshop. In particular, I will talk about diagrammatic Monte Carlo calculation and numerical compression of interactions in condensed matter. So my group and I work broadly on first principles calculations of electron interactions and dynamics in materials. We use density functional theory as a starting point to study the electronic structure of materials. And then on top of that, we employ primarily Green's function and many body techniques to study interactions and dynamics. Today we'll focus primarily on the interactions between electrons and atomic vibrations, aka phonons, but we work on a variety of degrees of freedom in matter, including the coupling, spin, exciton magnons, and so on. Once we have these accurate interactions, we typically study a range of transport phenomena and non-equilibrium physics. We also develop a popular open source code to do these calculations efficiently. So just to introduce this topic, as you know, as the atoms move due to their thermal motion, they perturb the potential seen by electrons in solids. And so this perturbation, you can write this electron-phonon Hamiltonian, essentially tells you that in lowest order theory, the effect of this potential is to scatter electrons between an initial state with a certain band n, crystal momentum k, into a final state by emitting or absorbing a phonon. And so the scattering amplitude for this process, which is the electron-phonon coupling matrix element, is the central quantity in the theory. And with methods based on density functional theory, we can not only compute it, but also resolve these scattering processes for different electronic states and phonon modes in momentum space. And that's a first major advance relative to conventional electron-phonon theories. So once you have the electron-phonon coupling, then you can set up your field theory. Essentially, you have your electron Green's function, G, phonon Green's function, D, and the vertices, aka electron-phonon coupling. And so you can form diagrams of high orders. This is the lowest order one, also known as Van Migdal, which works when the electron-phonon coupling is weak. There is a whole workflow and machinery to do these calculations. We're starting from density functional theory. You initially form these interactions in momentum space, a relatively coarse grid, because that's all you can afford. But then if you remove the known long-range coupling, you can take the short-range part and interpolate it to very dense momentum grids. The way this is done is by first transforming into a localized basis, which are typically 1E functions, where these interactions are essentially hopping integrals that decay rapidly. And so with a double Fourier transform in both the electron and the phonon variable, you can interpolate to extremely dense momentum space grids of order 100 by 100 by 100 or denser. And then that's essentially the starting point to study transport and dynamics. And this workflow is general to other types of interactions as well. Now, once you reach this step, typically, these calculations end up computing billions of these matrix elements. They're not free parameters in the theory, they're computed, but that's what really makes this workflow so heavy. Now, however, we're in a much better position than we were 10 years ago. So now calculations in simple semiconductors of metals, of transport properties, in magnetic field or versus temperature doping or spin relaxation times or non-equilibrium dynamics and spectroscopies. These are things that for simple systems can be computed quite routinely. To share a couple of examples, if the electron-phonon coupling is weak, you can compute the time scale for the scattering processes for each electronic state, basically using Fermi's golden rule. And you can use the Boltzmann equation to study transport properties. Just to show you an older work, in 2016, for example, we showed how to introduce the long-range electron-phonon coupling in these calculations, and that allows you to predict transport properties in polar materials but also understand the underlying mechanism with a high accuracy. For example, this is the time for an electron in the conduction band of gallium arsenide to emit an Electron-Phonon, and it's predicted within a few % of experiments. I could go on with the list of things that you can do, but for example, if you add spin-orbit coupling, you can look at the spin-flip mechanism, and that allows you to, in this case, add up billions of spin-phonon interactions. For the spin, each one of these is the order of a nano electron volt, but when you combine all these numbers without free parameters in the theory, you can predict spin relaxation times in many semiconductors in beautiful agreement with experiments. Now you can do this for systems with up to tens of atoms in the unit cell. But everything I've said so far essentially pertains to the weak coupling regime. And if you increase the coupling strength for the electron-phonon interaction, the electrons become strongly coupled with the lattice. They form so-called polarons, which are essentially entangled states of the electrons in the lattice. When the coupling has an intermediate strength, the electron is still delocalized, and we call that a large polaron. And there's signature of those effects in the spectral function. In the limit where the coupling is very strong, the electron localizes. It obviously pays a penalty in kinetic energy by localizing an electron in a solid, but the coupling with the lattice is so strong that it localizes the electron and forms a so-called small polaron. There's a variety of first principles techniques to describe polarons, but typically they tend to focus on the formation energy. For example, you could take a very large cell in density functional theory, slap a charge inside, and it's a very backhanded method because it's error prone. You need corrections. DFT often misses how localized states are, but it allows you to estimate whether or not a polaron forms. Here, I'm trying to answer a different question, which is computing polaron dispersions, spectral properties, and transport properties. So our first encounter with this problem was working on oxides. Basically, many complex oxides or perovskites or other classes of systems have electron-phonon coupling with intermediate strength. So, for example, this is cubic strontium titanate, and you see that if you map the strength of the coupling on the phonon dispersions, the strongest coupling is with these longitudinal optical modes, which generate a long-range electron-phonon coupling. It's basically an oscillating dipole. This is called Froelich coupling, and because it's long-ranged, the intuition is that it tends to form large polarons. Now, in this paper, we focused on accurately including also the low-energy modes, and basically, if you use lowest order theory in the Boltzmann equation, you can predict the temperature dependence in agreement with experiment, but the mobility is overestimated by an order of magnitude. And the reason is the coupling that you're using is too weak. It's basically missing terms that are crucial to describe the polaron. So then, at the time, what we decided to do is to just add more diagrams. There's a method that is called cumulant in this context, where you basically use an ansatz for the Green's function. You set it equal to the non-interacting one times e to a function that you call cumulant. And the beauty is you can compute the cumulant with the lowest order self-energy, but then because it's exponentiated, it gives you a whole series of diagrams, but only this family of improper diagrams. So this method was actually pioneered in the context of electron-electron interactions, where it's known that GW, which is the equivalent of this lowest order diagram for the electron-phonon, cannot describe the satellites in the spectral function. And it's known that this method actually can improve the description of the satellites. And so when we applied this method to the electron-phonon problem, for example, you can take an electron in strontium titanate, you see that if you look at the spectral function next to the peak at the band energy, you find the emergence of two satellites due to the strong coupling with the electrophonons, and the most pronounced one, which is at about 100 milli-electron volts from the band energy, actually matches extremely well ARPI's measurements. That's encouraging, but also now you can use Green-Kubo theory, so obviously a more general quantum mechanical framework, and you can use a spectral function that includes polaron features to compute the transport properties. And when you use this cumulant plus Kubo method, because the quasi-particle loses spectral weight, the mobility drops, and now you can predict with a high accuracy both the temperature dependence and the absolute value of the mobility. So with this method, we've applied it in the large polar regime to a range of oxides, organics, and so on. But we also know that it has some shortcomings. In particular, it's known from models that it works well at small momenta. For example, if you trace the peaks of the spectral function, you see that relative to DFT, this essentially increases the mass of the polaron, which are these dispersion curves, but then it has this artificial endpoints where basically the peak of the spectral function melts. And that's a problem of this technique. We also know that it always predicts a power law for transport. So it can only describe the metallic regime, and it cannot describe the small polaron and the hopping regime. So a couple of years ago, with my student Yao Luo, we thought that we could maybe add up all diagrams.
Sorry, maybe I'm not quite familiar with this technique. So I guess typically we think to take the self-energy diagram, the Fock sunset diagram, and resum in terms of self-consistent Born approximation so that your Green's function is the one that's involved after the self-energy correction. How does that compare to this cumulant that seems to not be self-consistent?
Yeah, so you could do that like a Van-Migdal quality spectral function. It would describe the quasi-particle peak accurately, but it would miss the satellites. That's like a known fact. Because it does not add higher contributions like the cumulant does. Mm-hmm. So the idea of diagrammatic Monte Carlo is that you just add up all diagrams, I'll put that in quotes, in this case for the electron-phonon problem. So how do you do that? You basically create a Metropolis Monte Carlo algorithm that sums diagrams in the space of different topologies and different diagrams order and sums over internal variables. And this has been done for models before. For electron-phonon model Hamiltonians with just one electron band and typically one phonon. There was a question.
Sorry, following up on John's question. So these cumulants basically take into account corrections to the phonon propagator or vertex correction?
Those would have to be taken into account separately. So this is a correction mostly to the electronic sector, to the Green's function of the electron.
Still phonons are bare phonons, and
the phonons are bare phonons, but in most systems, they're typically good enough. From density functional theory, you can compare them with experiments, and it works. And when it doesn't, it's usually because of inharmonicity, and rarely because of the lack of electronic correlations.
I see. So how about the vertex correction? That's also absent, or that's inside this cumulants?
The vertex, you could consider correcting how you calculate G, the electron-phonon coupling with a vertex, and that's some work on that, where, for example, you could take derivatives instead of the constant potential of DFT of the self-energy. Mm-hmm. So in GW, there's been a long tradition and a discussion in the community that lasted for many years of how to construct the diagram. And there is an agreement that one should use the best G and the best W. So here you could argue you could use the best electron Green's function G, the best vertex lowercase g, and the best phonon line. And so, but at that level, basically, it needs to be done on a system-by-system basis.
Right. Yeah. Okay, thank you.
Okay. So for models, when you have only one band, diagrammatic Monte Carlo works. You can set up like a Holstein model, a Froelich model, and it's been done before in this pioneering work. However, if you look at the electron-phonon Hamiltonian, you basically want to solve for the eigenstates, the polaron. What you could do is you could focus on the electron propagator that is basically dressed by an arbitrary number of phonon lines. Okay, so if you work in imaginary time, where the Green's function is smoother at zero temperature, you basically add up these amplitudes, which are Feynman diagrams for the electron-phonon coupling with arbitrary number of phonons. However, for Monte Carlo to work, this quantity has to be positive. And the real challenge, and you really have two to do this from first principles, is first of all, the electron-phonon coupling now is a matrix and it's complex valued, unlike the models. So there is no guarantee that this object is going to be positive. The second one, the sheer cost of computing G, the electron-phonon coupling in momentum space as you sample, is just insurmountable. And so we know people that have tried before, and you basically give up because you think that it's just impossible. So I'll show you our progress on this, and particularly using diagrammatic Monte Carlo to compute polaron dispersions, formation energies, and also look inside the polaron to look at the dressing from the phonons and transport properties, both in the small polaron and in the large polaron regime. So first of all, you can implement the calculations for a model. And in that case, you get the ground state energy in the infinite limit of infinite imaginary time. And so we can do that, and then we can get results that agree with previous work. So you can get total energies and dispersions also for simple models, but G is always positive in this case, so the integrand is also positive. The real problem is here when you want to do it from first principles because of the band indices. So if you just took what's been done before for models, you would be sampling this integrand D. You cannot sample D per se because it turns negative. And so you just take the absolute value. If you do that and you sample the band index as part of the internal variables, that turns into a disaster. It's basically a long times. The error is far greater than the value of the Green's function, so you cannot extract any energy. You could track the sign of D, and the reason it happens is because D quickly becomes negative, or somewhere between positive and negative, close to zero. The idea that my student Yao had was to treat this one as a product of matrices. Okay, this is a product of Hermitian matrices, and it turns out that the trace of products of Hermitian matrices, there is not a theorem, but it's at the level of a conjecture, is very often positive. There are some cases where it's not, but it's the vast minority of cases. So then what you can do is you can sample the real part of the trace of D. If you do that, and you basically don't sample the band index explicitly, you just do the product of the matrices, now the Green's function is very well behaved, and the underlying reason is that this object is mostly positive. So this solves the sign problem for electron-phonon DMC. It's different from the problem in quantum Monte Carlo, so it's not that sign problem, it's a different sign problem. So we have that under control, and now with this method, we can basically compute polaron formation energies. You can compare just the DFT bands and the diagrammatic Monte Carlo bands. Polaron dispersions, so effective masses, and also you have polaritonic effects where the electron-like dispersions of the polaron become phonon-like, which you observe at the limit of the one phonon continuum. If you compute a different Green's function, the one that has external phonon lines, you can also look inside the phonon cloud, so to speak. So this is in a way similar to Kavli QED, where you have states dressed by photons, but here instead the polaron is dressed, the electron is dressed by phonons. And so you can sample this distribution of how many phonons you have in the polaron state. And so this is a hole carrier in lithium fluoride that essentially forms a small polaron. And you can see there's a Poisson distribution, and on average, there are 26 allophonons in the cloud. And you can actually turn off the long-range coupling and establish that half of the formation energy comes from long-range and half from the short-range coupling, which is a little bit counterintuitive for a small polaron. And you can do similar things in the large polaron regime, looking at how many phonons and which ones contribute to the polaron cloud, as well as look at the electronic contribution to the polarons. There was a question over there.
It seems to me that the essential thing is this separation into product of matrices. But this is not necessarily unique. So how exactly do you do it?
Not necessarily unique, as in...
It is unique. Or is it?
So basically, like for each diagram that you're adding, because you're sampling, suppose that you make a trial move that generates a different topology and a different order. That diagram, you have a time-order Green's function, so the order of the product is well-defined, and you just multiply these matrices, which are the Green's function, basically the building blocks of the field theory. The Green's function is a matrix in band space, and so is the electron-phonon coupling G. You do the matrix product. These are all Hermitian matrices. Then you take the trace, then you take the real part and the absolute value.
Okay. Yeah, I see. Good.
Thank you. But so now you can sample a different family of diagrams where basically from the current correlation function, also you can sample it to all orders. Now, the problem is you can basically compute the optical conductivity, but that is under an integral, so you need to extract it from analytic continuation. And so there's a way to basically estimate the error that you do when you use analytic continuation. I wanted to show you the case of rutile because it's a small polaron system. And so in models, it's known that first the mobility should drop, but then there should be a regime where it's thermally activated and it goes into hopping and then it saturates. Now, experimentally, this has only been measured in the metallic regime, but our DMC prediction no longer it can reproduce the metallic behavior, but at higher temperatures, it can actually capture the upturn of the mobility that's missing in the cumulant, and so describe the thermally activated and then the saturation regime. There were two questions. I'll start with the one in the back.
If I understand correctly, the important computational breakthrough is that you compute the trace of D rather than the determinant. Is that a controlled thing to do? Like a okay thing to do?
So, okay. Thank you for the question. I will note that I've not described it as a breakthrough, but thank you for saying the word. But so I'm not claiming that this is always going to work, but basically the trace of a product of Hermitian matrices is almost always positive. And there's a conjecture on that, and we started talking to people who know more math than we do. And apparently when that doesn't happen, you can have a negative sign, but there's usually a topological reason behind it. These are the kind of things that basically, so first of all came the matrix product, which is a convenient practical hack. And then you have the matrix product, so what do? You take the trace. And Yao discovered that this works in practice, and then we try to understand why, but it really does.
Sorry, so just to make sure, so this technique is essentially for calculating the effective action for all diagrams of that type shown, where you have one electron propagator and as many phonons as you want, but this then misses some effect due to the electron-electron interactions mediated by phonons?
So basically, exactly, like it's important that there are no two electron lines, otherwise you would run into the fermion sign problem. So it's always one electron in, and it's either that you have n phonons inside, or you have also n phonons in and n phonons out. So we're doing both processes for different reasons, and we sampled them with this method.
Mm-hmm. Okay, thanks.
And then finally, this is a different phase of titanium dioxide, anatase, which is typically grown in thin films by stabilizing it with strain. So we wanted to study this material because we had studied rutile, and so we made this prediction using DMC. So this is this system has a large polaron, so it has mobility that decreases as a power law. Then we talked to our collaborator, Bharat Jalan from University of Minnesota, who has grown probably one of the highest quality thin films of titanium dioxide using MBE. So if you look at previous experiments, you see that his sample has the highest mobility ever realized. But it's important here that the theory basically came before the experiments. And so as you can see here, within the error bar, due to analytic continuation, you can very accurately describe the mobility in the large polaron regime. Now, we think that this might be just the first of many diagrammatic Monte Carlo methods that we can realize, each one with different challenges. But for example, we work also on exciton-phonon and magnon-phonon coupling, or the enharmonic phonon-phonon interactions. Each one of them would require a different way to sample diagrams and a different way to speed up the calculation of the couplings. But in principle, this could be an area that could have intersections, which one of the interesting themes in this workshop, which is terahertz or infrared cavities, which we know nothing about, but we'll be very excited to hear, whether this method can be applied there in useful ways. So in the last 5 to 10 minutes, just to lighten up the talk a little bit, the second reason we got DMC to work is surprisingly related in a tangential way to the crash of the stock market that happened last Monday. This was not the tariffs. Surprisingly, it had not to do with the new administration. Rather, it is a company from China called DeepSeek that has released a method and a code that can perform neural language processing orders of magnitude faster than ChatGPT. So maybe you don't need all the chips in this world to run these algorithms. The way that's achieved is by significantly slashing the number of parameters that are needed to train the network. And so this compression in parameter space essentially speeds up this method, and it shows you that there's an inherent sparsity. So there's only like several parameters that are important, but not all of them. This idea is kind of a common theme that sometimes people call Occam's razor, which basically you should find the best model that also uses the minimum number of parameters. And there's a sweet spot that people call a Pareto optimal model, where you can both minimize the complexity of the model and the error. So to think about that, we turned to data-driven methods, in particular a method that many of you might be familiar with, singular value decomposition, that is widely used to compress matrices and images. So SVD is basically like diagonalizing a matrix, but a rectangular matrix. So you decompose it into the product of, in this case, 2 different unitaries, and then you have a matrix that has diagonal entries that are positive reals that are called singular values, and you can arrange them in order of how important they are. When the singular values decay rapidly, you can sample just a few of them, and then when this method works, you can basically, by using just a smaller fraction of singular values, you get the best low-rank approximation of a matrix. In this case, even at 1% or 5%, you can still make out the details of the image. This is used in different areas of physics, including quantum information science and so on. The question we asked in this recent work is whether you can actually use to compress the matrices that represent interactions in condensed matter. And so, to our surprise, we discovered that this works extremely well, for example, starting with the electron-phonon interaction. We removed the long-range part because it's just due to electromagnetism, so there's nothing to compress there. That's what we found out. But if you focus on the short-range part, in the 1A basis, these matrices are typically the size of like 1,000 by 1,000. So you can do SVD, and you realize that the spectrum, where you essentially separate the electron and the phonon degrees of freedom, decays very rapidly. And so you can keep just a small portion of the singular values, and they give you accurate interactions. What we found is that only the short-range part, which is really the one that you need DFT for and quantum mechanics for, can be compressed. And so that's consistent with Walter Kohn's insight into the nearsightedness of the electron structure problem. So what's the saving? Well, the reason is we still need to work with the dense grids in momentum space, but now transforming from the real space, the compressed one, to the momentum space has a cost saving that is proportional to the fraction of singular values. So if you use 1% of singular values, you basically save a factor of 100. The reason is that you turn this double Fourier transform into two separate single Fourier transforms. The question is it accurate enough? And so here, I'm showing the entire Pareto frontier, basically error versus fraction of singular values. And it turns out that at 1%, about 1.5% of singular values, the error is about 1 to 1.5%. And so this is almost like a lossless compression. You could say that is Occam's razor or DeepSeek in action. And surprisingly, you can basically run all of the calculations that I've shown, or like most of the calculations on Electron-Phonon that the first principles community is doing, including mobility, spin relaxation times, superconductivity, polarons, with about 1% of the singular values. So with a speed up in explicit timing tests of order 50 to 100, factor of 50 to 100. The reason it works is related to the fact that this method finds pattern that you didn't know a priori. For example, in silicon, if you analyze the first singular vector, it shows you that it's just a bond stretching, but that's an insight that you didn't have before. So potentially this method could help you come up with simplified models starting from the whole first principles workflow. And finally, because of the way the coupling is sampled in D and C, actually the speed up for that algorithm is the square of the speed up in this calculation. So this basically makes diagrammatic Monte Carlo possible because it speeds up the algorithm by a factor between 1,000 and 10,000. So that was the second, besides the sign problem, that was the second key piece that was missing. I will wrap up in just 2 minutes. I wanted to show you that this is not exclusive to electron-phonon coupling. We think that there's room to compress many other interactions in condensed matter. For example, if you write the usual phonon Hamiltonian and you expand to third and fourth order in the atomic displacements, these interatomic force constant matrices are known to be typically short-ranged and sparse. But the question is, how do you go about compressing them? So for the third order, which in momentum space is basically 3 phonon scattering, you can set up singular value decomposition by taking advantage of translational invariance. And so here, similar game, you can show speed up of maybe like a factor of 50 or so for phonon line widths or thermal transport calculations, but you cannot decompose higher order phonon interactions. And so in recent and still unpublished work with, still with my student Yao Luo, we started using tensor decomposition methods that are typically used in machine learning. This is a tensor decomposition ansatz that is called PCP. The usual method is CP, but we have adapted it to be permutation invariant so that if you change the indices of the momentum, this does not change. The beauty of this decomposition is that it's exact in the limit of where the rank goes to infinity, but you can truncate it. And when you truncate it, you basically need to learn somewhere the functions AI, which are attached to each momentum Qi. So if this is a 3 phonon or a 4 phonon potential perturbation, this would have 3 or 4 momenta, but n-1 are free because of momentum conservation. So because it's 2025, the learning is done with machine learning using PyTorch, running on NVIDIA GPUs and so on. But the gist of it is that you're basically learning these matrices from the interactions on the coarse grid. But then once you have them, you can interpolate. And so here, this is really striking, I think, because SVD, in this case, saves you, if you look at the interactions at the 3% error threshold, for example, right? SVD saves you maybe a factor of 100, sometimes more. But this method, this tensor decomposition method, saves you more like a factor of 1,000 to 10,000. So it finds the sparsity in the microscopic interactions. And in explicit time tests, this is the 4 phonon coupling, which can be computed currently only in hero calculations on extremely sparse grids. This one you can do on grids that are 100 cubed in seconds, and it provides a speed up of over 1,000. So basically, we're finding the extreme sparsity in interactions in condensed matter. And I just wanted to conclude with a slide on our code. We have recently released a new version of our Perturbo code, which includes some of these advances. And it can also now be run on GPUs. It will basically extended most of the functionalities toward quantum materials, so systems with non-trivial band topology and or electronic correlations. And so these types of tools are forming a community within the first principles field that uses this method to study materials. So I wanted to thank my group, but in particular, I wanted to thank Yao Luo, who is the mastermind behind both the compression work and the diagrammatic Monte Carlo, and shockingly, he's still a third-year graduate student. So to conclude, because we don't have cavities, we had to reach the strong coupling limit, summing one diagram at a time. So we're jealous of the experimentalists, so with this method, essentially, we can access quantitatively polaron energies and dispersions and transport in the polaron regime, look inside the polaron and the dressing and so on. And there's hope to extend it to other types of interactions by taking advantage of these compression algorithms, which we're trying to generalize to other forms of couplings in condensed matter. Sorry for going a little over time, but yeah, thank you.
So I guess I'll keep going. But so if essentially this technique is, I mean, basically my question is, what is the benefit of momentum space actually if presumably the interactions are very local, as you said, in real space? I mean, you're throwing away the long range part. You have like a few short range Hamiltonian parameters that are local on a lattice. So is that not what the system is discovering?
So yeah, I mean, it's true for the polaron. When it's a small polaron, ideally the dispersion is nearly flat. But most real materials do not fall exactly in that regime. There's basically, there is a dispersion, there is a mass enhancement of the electron, and this method can quantify that in the entire Brillouin zone. And when you compute transport properties, you're essentially sampling that dispersion. And you're also inherently sampling the spectral function and how the spectral weight has been redistributed. The spectral function explicitly can be extracted, but it's from analytic continuation. So in some cases, in like simple cases, it may not be as accurate as the cumulant, but basically you don't need to go through the spectral function to compute transport, unlike the cumulant method. So there's no green kubo, like you're basically sampling directly in momentum and frequency space the current correlation function, and so obtaining transport properties for that. So for that, you need momentum space dependence as you do for like masses and dressing and so on.
Okay, thanks.
Thank you. It's a great talk. So my question is, whenever you talk about it, like strong couplings, what is this strong coupling between an electron-phonons comparing to the electron-electron coupling in the reference strands when you perform the calculations?
Okay, so in principle, you can have both effects, right? The effects can coexist. If you're in a strongly correlated metal, for example, you can have strong electronic correlation, or like in a strongly correlated insulator, but it can also be polar, and so you have strong electron-phonon coupling. Typically, when the electron-phonon coupling is strong, it's because you have long range, either Frolic or piezo, or both. The polaron, however, is due to a combination of effects. So it's, for example, it's present in organic materials which are not polar, and there's nothing long range. But from the models, it's actually known that it's due to a combination of the electronic bandwidth and the value of the coupling strength. So on this axis, I basically put both the electron-phonon coupling strength G, but also the band flatness, which is an aspect that I've not discussed. But G can be weaker, but if the bandwidth is very small, you can still have polaron effects, which I would still classify as strong electron-phonon coupling. So the electron-electron changes band structure, the quasi-particle spectral function, and the electron-phonon can be compounded to that.
So if I understand correctly, the electrons should be very close to equilibrium here. So how easy is it to generalize it to the non-equilibrium, like highly non-equilibrium situation?
So yeah, this is like this is basically for the transport. This is a linear response formalism. We've not tried to go beyond linear response, but in principle one could. You just need to compute a different correlation function and sample it.
Can I ask about the interaction compression? I think I just missed it. Like you start from saying there's long range, there's a short range, and you compress the short range. What happens to the long range? And like, is it possible that's short range in like a different basis, or is that just?
Yeah. So basically, in all these calculations, we know the form of the long range, which is either dipolar, so frolic, and or quadruple. The standard interpolation technique works by first removing them on the coarse grid, then interpolating the short range part, and then adding them back in momentum space. But they're very easy to compute because we have their expression in closed form, but with parameters computed with DFT. So here you could take the entire thing constructed on the coarse grid and try to compress it, but the spectrum of the singular value would decay very slowly. And then you realize that when you take out the long range part, actually becomes highly compressible, and there's no cost in adding back on arbitrarily fine grid the long range part.
In the end, you mentioned that you're able to treat systems that with the truncation that are much larger than what conventionally possible. How do you judge these error limits in those cases where you have no untruncated solution?
So the truncation, like conventionally possible, I want to be careful about thinking about that because basically nobody has done this work before of like building these matrices with all the band indices and so on and trying to compress them and look at how compressible they are. So I will just say that so far the systems we have encountered, the vast majority of them, you only need about 1 to 2% of the singular values. There are some subtleties. For example, this C means constrained SDD. You have to be careful about what you're compressing. For example, in silicon, the electron-phonon coupling with the acoustic modes, as it's often the case, is weaker. And so an algorithm like SDD will tend to discard it. However, you can come up with a different form that preserves the coupling for the acoustic phonons, and you can compress that one. So basically, when the weaker interactions have a predominant weight, because they matter for the kinematics, so they matter in phase space, then you need to be a little bit careful because this thing might just discard them.
Just a quick question. So could these learning methods be applied to experimental data, like to learn like the phases of matter from the experimental data, basically in solid state systems?
We have not tried that. I mean, in different contexts, like people use ansatses like these ones and different ones to infer from experiments, learn, and so on. In terms of just interpreting, if you mean microscopic interaction data from experiments, nobody has probably tried that, but in principle, one could.
Hi, thank you so much for the talk. I want to ask for this wonderful new method you developed, the Monte Carlo simulator. Can you say something about the scaling of the computational cost with respect to, say, diagram order or the number of KQ points or number of bands and so on?
Oh my God, it's definitely in the paper, but it basically, I think that the cost should scale as the product of K and Q, because that's the space where you're summing. And that's also the reason why there is a speed up that is the square of the other calculations. Like typically, if you want to compute the self-energy at K, you sum over Q, and so you can do the interpolation only over the phonon variable. That gives you a speed up of a factor of 100. For DMC, the speed up is square precisely because it scales like the product of NK and NQ. The order, basically you're sampling according to D, right? So you make the move, and then you look at the value of D, and you decide whether or not you're going to reject, right? So if at some point, well, after you simulate, you can look at how the different orders have contributed. but it typically dies off, right? And then if you start sampling very high orders, the moves will get rejected, and so the algorithm will go there less commonly. So I think it's hard to attach, like a scaling factor for the order, but basically the algorithm will find how the different orders are important just through the sampling process.
Thank you.
And if I, oh, sorry. Yes. Yeah, and if I may ask, I mean, it just might expose my, my ignorance, but look, one other technique which I understand is good when you have strong interactions, NEGF, non-equilibrium Green's function. I mean, are those techniques that you developed could also be applied there, where I know that the computational burden is also enormous?
Yeah, so I would say for the non-equilibrium Green's function, it's more of a method for the dynamics. So basically, one could take the interactions and plug them into non-equilibrium Green's function, and that would be equally as useful as when one is using Boltzmann or Green-Kubo as they would for the non-equilibrium Green's functions.
Other questions? Well, if not, I think perfectly on time. And thank you. Thanks again for the great talk. And and let me